Today we'll talk about basics of nanotechnology. What are the basic concepts? Before we get started, here's the outline of the course. We will be talking about a bunch of things. I have grouped them under specific modules with similar concepts. So this is given in the syllabus. There's a paper that's been posted. It's called There's Plenty of Room at the Bottom. And there's a homework that goes with that paper. So please take a look at that. This was a seminal paper. Basically, it was a talk given by Dr. Richard Feynman, who was a professor at Caltech. And later, that his talk was published, compiled as a more of a his. He talks about many things, and this was late 50s when he gave that talk. So when you read, you'll see. We'll talk more about that as we go along. So where did it all start? We talk about nanotechnology. There is a history to that. At the start of the century, there was specifically the government, US government started investing in what they called as National Nanotechnology Initiative. And if you look at the data, the rest of the world was also spending about the same amount in 1998. So here's some data about US, Europe, Japan, and other countries. And you would see that US was spending much less than other countries. Even Japan was spending more in 98. But in 2000, major funds were invested in the area of nanotechnology. So, and then we see a spike. The rest of the world was not too far behind. And is if you see by 2002, many other countries started investing similar amount. If you think about it, even Japan more than doubled their investment in nanotechnology, going from 2000 to 2002. And by 2003, yeah, rest of the world also followed up. Why was everybody investing? Today we are seeing the results because those who invested, they are far ahead in the nano industry. They are far ahead in manufacturing at nano scale or using nanomaterials in various products. And this is something which we'll see as we progress in this course. What are some products that are already seeing major impact, especially when you talk about biomedical engineering or biotech. Now, what is nanotechnology, or how do we define nanotechnology? There is a specific definition which says that if a system, any one aspect of a system ranges in the size scale of 1 to 100 nanometer, we would call it nanotechnology, or we would consider it to be part of nanoscale regime. And now it's been about 2 decades that major investment was done all around the world. Today we have such a variety of knowledge, such a variety of activities that you cannot contain it into one department or even one book. There are multiple books which cover different aspects or different devices or different applications of nanotechnology. And something which is interesting is that electrical engineers have played a major role in developing nanotechnology, and more importantly, because of micro devices. We call them micro devices, but they are essentially nano devices because they have nanoscale features in it. The most important devices are solid state devices, computer chips, which are now in every device, starting from your bedside alarm clock to your cell phone to your uh, earpods, even light emitting diodes, LEDs, so which make up normal lights in our rooms now. They all contain that. So this fourth bullet points, conventional optical lithography, this is something which we'll read a little bit on that. And we will see that this is a process or technology, what we call optical lithography, that has given us devices in nanoscale. So by the turn of the century, we were already making 100 nanometer devices which went into our computer chips. I keep on saying computer chips, but you have to remember that's just a reference to integrated circuit with those chips which go in every device, not just computers. So by the end of 20th century, we were making 100 nanometer devices easily using 193 nanometer lithography technology. Don't worry about it. We'll talk about that later on when we go. But if you think about it, nanoscale features have always been there in living systems. This picture is very interesting. It gives on left-hand side all the things in nature, on the right-hand side things which have been made by human. This is an old picture, but it holds the same concepts even today, just to understand that in living systems, blood cells, uh, 2 to 5 micrometer, this should be not mm, it should be millimeter. Sorry, it should not be millimeter, it should be micrometer, where it says red blood cells. And when you go down to proteins, DNA, even virus today, virus sizes are 200 nanometers. So COVID is 180 to 200 nanometer dimension of that. So they exist in nature. But now, after so much work, this is few years old picture, but even then we were making things at micro scale very easily. So micro scales are what you call MEMS, micro electromechanical systems, which are like an accelerometer in a car, already been there. And then we have been making carbon nanotubes. We are using them as electrodes. This is a picture, it didn't come out well, but there are, and we'll see many examples of that. There are carbon-based materials which we can create at nanoscale, very, very small material, very, very small features, routinely made to carry out different roles in our life. It's an interesting picture here, which is from IBM, which shows individual atoms which are placed, which were in a using special equipment were brought to be uh, placed in kind of a circle shape. So that was achieved more about 2 decades ago as well. So there are things which have always existed at nanoscale in biology, and now we are creating those things at nanoscale with what we call as man-made or synthetic. So now, where does the inspiration come from? Everything is built up of atoms in whatever we look around. Now, those atoms, can we control them? We can control them in bulk, but the goal of nanotechnology is if somehow we can control probably each or few atoms at a time to get something important. What are those important things we want to achieve? We'll talk about that later on, but today we'll just stick to size and scale. How small is nano? If you think about it, it's the size of a molecule, of one atom, maybe. It's a billionth of a meter. What does it mean? We'll see the scale as well soon. If you think about a human hair is 100 micrometer, about 80 to 100 micrometer. So this is then uh, from a human hair, this is further 100,000 times smaller than that. And if you would to contain micrometer, which is 10 raised to the power minus 6, if you would contain 1 micrometer, 1 cubic micron water, that would have 90 billion atoms in it. So these are some plays of numbers, but the idea is to get you some feel of how small are we talking here. A sheet of paper is about 100,000 nanometer thick. Today we do uh, 3D printing. So this is an example from 2001 where they were writing micro scale features. So it used to be called stereolithography, but the idea is that we can write using multiple beams. We could write micro scale features. Now, we're talking about human hair. A human hair, this is a real picture using an electron microscope of human hair. So you can see the scale bar is 50 micrometer. And if you compare that, so this human hair is somewhere probably 70 micrometer. And then you see a thing which is lying on top of human hair. This is a carbon nanotube. So that should give us a perspective of how small are we talking, or how smaller than a human hair are we talking? So this thing, if you can see, this is carbon nanotube, which is lying on a human hair. This is uh, just to show, give an idea of what is the kind of difference in thickness or scale we are talking about. How do we convert in scales? Yeah, if you have to, from a meter, for example, if you have 1,000 meter, we call it kilometer. If you would have something 10 raised to power 6, we call it mega. For example, hertz to megahertz. If it's billions of something, we call it gigahertz, right? For example, from hertz to gigahertz. So, and teras, we know tera or giga in terms of our computer storage, gigabytes, and then terabytes, TB. So it's nothing but 10 raised to power 12. 1 trillion is what you call as terabyte. But when you go on the other side, when you divide these things, when you do division by 100, we call it centimeter. But when you do division by 1,000, we call it millimeter. Similarly, when we do division by millionth, we call it micrometer. 10 raised to power minus 9 is a billionth divided by billionth. 1 billion. So that is what you call as nanometer. And then pico, femto, atto are further smaller than that. So if I were to take a scale from my desk, I would say, okay, a scale has two measurement. One is inches, one is centimeters. So you take 1 inch, which is about 2.54 centimeter, and then you can chop it, and that would give you, of course, we cannot chop it, but we have to conceptualize and visualize how small are we talking here. So we would then take a centimeter and break down it into, so centi is 10 raised by minus 2, then you should be able to go from centi to meter and meter to, again, micro and nano, uh, if that's easy for some of us to get started. All right, so now just to put things in perspective, a normal human, uh, somebody with, this is a character from a movie, Mini Me, must probably a meter in height. If you look at the eyes, probably a centimeter. Then from centimeter, if you talk of a retina chip, maybe implant, would be a millimeter. And then you further divide it another 1,000, you would end up with what you call micrometer. And micrometer are moving chips, moving parts in that chip, what we call as MEMS. We further divide it into another 1,000, we get nanometer. So that's the man-made things. On the right hand side, we see again living things which are already existing in nature in many of those size scales. So this concludes our basic introduction to the size and scale and how do they relate with each other.